All right. So we are going to continue with our work from where we left off in the notes packet and the PowerPoint. So the last thing we talked about, I should have shown one more slide before we stopped. The last thing that we had said was because of a discrete random variable, it can be a function. So we talked about like finding a point versus finding a line or any other formula that you have available. And so, you can make a function x minus u squared, right? Like that's how we find the variance, is that function, that f of x times x minus u squared is in fact our formula for the variance. So the expected value of that particular function is actually equal to the variance. That's just an example. It could be any type of function. Like I said, there's an example, I think, in your book where it's x becomes x squared. So anytime you're given a function for a discrete random variable, this h of x is representative of what that function would be. So instead of the expected value being x f of x, it's that function h of x times f of x. So whether you have it as constant values of a specific variable or you have it as a function, either way, the formula doesn't actually change. It's just instead of evaluating a single point, you're evaluating a function as you go. So we had talked about that on Tuesday. There was one more slide, and before we start into all of our different types of discrete distributions, and so I should have shown that on Tuesday. So this is giving you an example of that, of showing what happens if you are trying to find an expected value and the function is given as x squared. So then for all of these values of x, the h of x is at x squared. So we have 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, instead of 0, 1, 2, 3, 4. So this is the same bits in error in transmission we had looked at earlier. We had found the expected value of just the actual f of x. Now we're given at h of x in addition to the f of x. And so we have the f of x column, we have the x column, and the function is x squared. And so we can see the expected value calculated. And obviously it's different because it is now a function. Still, our cumulative distribution function can be shown in that progression. And I did mention, like in your homework where it asks you for the cumulative distribution function, like this is what it's asking for. It's asking for all of those values for those discrete values given. You aren't required to show that they sum to 1, but it's not bad to do a quick check and make sure they sum to 1 because that's what it should do. So the actual cumulative distribution function does not involve the addition. It just involves all of those discrete values. But yeah, showing that those first sum to 1 and then what the cumulative values of each of those are would be the correct answer for your homework. So in a discrete uniform distribution, we'll be looking at the shapes of these. If not in this chapter, we'll look at them in chapter 4. But a discrete uniform for a value of x, we can calculate f of x to be 1 over n. And the reason is because if all of them have an equal probability, so the binomial function is a special function where we only have 2 potential outcomes. And the Bernoulli of the binomial is when they each have an equal outcome. So in that case, you have a discrete uniform distribution with only 2 values of x. And so there's a little bit of overlap here, and we're going to see a little bit of overlap in a couple of our different distribution functions. But the discrete uniform means that everything has equal possibilities. So one of the easiest examples that you'll see in a book is a 6-sided non-weighted die. Now, you get to those like Dungeons and Dragons, like 20-sided die. They're all, I assume, still equally weighted, right? So 1 out of 20. I don't know, my kids have all different crazy dice in their collections. But the simple example is usually a regular 6-sided die, the most typical. And so any value, any f of x for that discrete uniform distribution would be 1/6. They all have an equally likely outcome that you would roll a 1 as it is that you would roll a 4 as it is that you would roll a 6. And so we can calculate our f of x. So that when that situation arises, when you have multiple outcomes, more than 2, because if it's only 2 outcomes, then we're doing a binomial. And if we're doing only 2 outcomes with equal likelihood, it's a Bernoulli binomial. But if we're looking at more than 2 and they all have a equal probability, then we have a discrete uniform distribution. And the shape of that is not bell-shaped. It looks like this. It's just a straight line going across because they're all equally likely. So we can calculate the mean and the variance of a discrete uniform distribution with these two formulas. So the mean is equal to b plus a, and so this is that range over 2, which again, you're averaging your high and your low, right? And then your variance or sigma squared is b minus a, so that's high minus low, plus 1 squared minus 1 divided by 12. Your textbook derives that for you and shows you how when you have the mean, and we know what the derivation for finding a arithmetic variance is, that x minus mu squared times f of x, right? Like we know how to calculate that for the expected value. And so to go to the variance, it is the same formula. So if you do v of x of that e of x, b plus a over 2, you will get this answer. Because this is one of the more popular distributions to be used, we just condense it down to a formula, and you don't have to go through the derivation to get there. Also, on your packet, the whole reason for having this formula sheet is so that you have a quick reference for all of these different formulas. I would keep it out while you're doing your homework to just have this out, and so you can quickly reference all the particular formulas that you need. And so if we look at our little graph here, our terribly drawn graph. So this is point A, this is point B, and so our expected value of x is equal to b minus a over 2, or I'm finding the mean, mu, on that line, right? That's what I'm doing. I'm just the same way I would take an average of 2 points. It's the exact same thing is what I'm doing here. So just a little visual for how that formula works. All right, so this gives an example. And so this says it's a discrete uniform variable with a range from 0 to 48. So 0 is your A, 48 is your B. I sum them, divide by 2 to find my expected value, which is, ta-da, 24, the middle number, right? And then to find the variance here, they're actually finding the standard deviation because we just are looking at sigma. And so it's the formula for the variance underneath the radical. And so we've calculated the expected value and the standard deviation. Be really careful with your homework. They will switch back and forth between what they're asking for. Sometimes they ask for the standard deviation, sometimes they ask for the variance. So be careful of whether or not it's asking for a sigma or a sigma squared, because they will go back and forth between what they're asking you for in your answer. Now, practical interpretation. Again, we're not mathematicians, we're engineers. A variance of 14. Now this is voice lines that are used. So this is like a call center. So imagine all these people spamming your grandparents and your grandparents actually pick up the phone and talk to them. So they've got 48 lines that could be used at any one given time, and they're making calls and they're making calls. And the average line in use, the expected value would be at any given time, you would have 24 of those 48 lines in use. But your variance for any singular given data point, or your standard deviation, sorry, for your spread, your dispersion is 14.14. That's huge. That's huge. Percentage-wise of your mean, that data is all over the place, right? So what is it? That's your robocalls, that's your going to voicemail, and so you get part of the message from the robocall and it clicks and hangs up really quick. And then ta-da, they get my parents, and my parents pick it up and have a nice long conversation with the individual, being very polite until they say no thank you and hang up. That's what this is, right? That's what this is implying. It's a highly variable setting. How do you staff that? Think of that. How do you manage a situation where you've got a mean of 24 and a variance of 14? Some of the times, absolutely nothing is happening, and then sometimes it's crazy. All the lines are occupied. How would you staff it? You're in charge. You're the manager. Well, so you could do what FedEx does. My kid's working at FedEx right now because it pays a lot more than the student worker. So he also works at Car, but he doesn't have a lot of hours at Car right now. So he's working at FedEx. You know what that's like, Charlie. um, But so he's working at FedEx right now, and they're getting ready for their holiday season. And he's scheduled for a shift. And if they don't have enough work, they just send him home. And so his schedule is highly variable. So he'll work 33 minutes in the shift or he'll work 6 hours. And it's just based on demand. If the demand is low, they just send their people home. That's how they've chosen to handle wide ranges of variability, is that their staff, their part-time staff, are not guaranteed hours. You might be slotted for up to 20 hours a week, but they're not guaranteeing that 20 hours a week. You work what you work based on what demand they have for their business. They're not going to have you stand around and not load a truck. That's one of the ways you can do that. So there are businesses where their staffing is highly variable because of highly variable demand, and that's how they handle it. They just send people home and they don't pay them. And that works for part-time employees, that works for contract employees and temp staff and things like that, is that you actually make adjustments based on variability. You see that sometimes in manufacturing centers as well, that when they ramp up, like Toyota, if they have a big ramp up, they're not going to hire more people. They're going to contract employees and they're going to put them on short-term contracts. And if they're good, they might end up hiring them full-time anyway. But if their demand decreases and the workers weren't necessarily that stellar, they just release them at the end of a contracted time as short-term employment to help address a specific short-term need. So addressing variability is something that we have to do in organizations all the time. And the way that we can address that variability changes based on HR policies. But if you're managing in an organization, if you're going in as an engineer and working and managing other people, staffing might be something that you have to keep track of, to think of, how am I balancing this line? How am I not wasting the company's money by having people standing around doing nothing? If you're a manufacturing engineer, for example, this could be something that you encounter quite a bit. So the binomial distribution, we've mentioned this a couple times. Binomial distribution is anywhere your probability is going to be between 0 and 1, as all other probabilities. But we're looking at a random variable X for the number of trials that result in a certain number of successes. And the next 3 distributions we're going to look at, the binomial, the geometric, and the negative binomial, are all derivations of this. This is the base formula, and dependent on what it is that you're doing, you can mathematically manipulate it for other things to just simplify your expressions. So the probability mass function of a binomial, your f of x, for finding an expected value or a variance, we start with the f of x, is one of these permutations. It's one of these counting things. So that n over x is that factorial. So that's n factorial over x factorial times n minus x factorial, right? So we're using our counting that we saw in chapter 2, and then we have a probability of success to the x times 1 minus the probability, which is in fact the complement, right? So again, we're using our probabilities here. We've got the probability of success and the probability of failure, because those are the only 2 potential outcomes that you can have. It's either a success or a failure. A lot of things in engineering are binary. A lot of things in engineering on off. Think of all of my, where do I have electrical engineers in the room? Couple? Okay, so all of your circuits, right? Open, close, on, off. Things are going or they're not, right? There's a lot of binary applications in electrical engineering. We see it all the time in manufacturing. We see it also in testing in our mechanical engineering situations. So this concept, the binomial distribution, is one of the most frequently used in industry. And what we love about the binomial is we can approximate the binomial with a normal distribution as long as n is greater than 40. So we like the binomial because its shape looks just like a bell curve. It's just slightly askew from a normal distribution, as long as we have a large enough sample size. So our probability mass function uses these concepts in probability. We're using our counting functions, we're using our law of the complement, and we're using our law of independence. The reason that I can just multiply these out is because these are random independent trials. So almost all of your homework questions are going to start with that verbiage. They're going to say, in random independent trials, the probability of success is this, the probability of failure is that. As soon as you see those words, you know that you are looking at a binomial, a negative binomial, or a geometric. Then, based on what they're asking you to find, we'll determine which of those three it is. But as soon as you see those things, only two potential outcomes, random independent trials. It's a binomial, a negative binomial, or a geometric. So the mean for a binomial is simply n times p, the probability of success times the number of trials that you have. Why? Because all of the trials are independent and random. So just what's the probability of success times how many times I'm going to do it. So I flip a coin 50 times. What's the expected value of the number of heads I get? I flip a coin 50 times. It can only be heads or tails. What's the expected value for my number of heads? 25, right? So it's probability times trials. So 0.5 times 50 is 25. So whatever the trials are, whatever the probability of success is, we multiply those together. The variance, again, this is derived in your textbook if you'd like to see why this is true, is NP, so our expected value, times 1 minus P, or the probability of a failure. So that's the binomial mean and variance. So we have the previous example, the number of bits received in error, a probability of receiving one in error was 0.1. And we had, we were looking at 4 bits. And so N 4, P 0.1, multiply those together, our expected value is 0.4. And our variance, N times P, that 0.4 times 1 minus P, or 0.9, that gives us 0.36. So if we're looking at the probability mass function as it is, then I can actually look at this binomial expansion as well. And so my binomial expansion is for all values of k from 0 to a given n, that total number of trials. I can look at the n over k times a to the k times b to the n minus k. And so you see that this is just a kind of revamping of the probability mass function in a binomial expansion. And so we do a couple of exercises of this. And one thing that's going to be important for you guys to remember that 0 factorial is equal to 1, not 0. 0 factorial is equal to 1. So when you're doing math, some of these answers will come up where you'll have 0 factorial in the denominator. And remember that that is equal to 1, not 0. So they give an example here, and they actually show that you can use Excel to calculate the binomial. You can also do this in Google Sheets. And so it's fairly easy to have this done. There is a couple things that we need to note because this false statement there for the binomial distribution, they're actually looking at the cumulative distribution function, or they're looking at the individual f of x. So we can look for the probability that X is equal to a given number, but the default setting in Google Sheets and in Excel is that you're looking for the cumulative distribution function. And so you have to write false in that statement to get the probability mass function, or in other words, the probability of f of x being equal to a given number. So otherwise, it's calculating the probability that x is less than or equal to 2. In other words, the cumulative distribution for that given value. So again, we see that we have our n over x for counting. So our n number of samples analyzed was 18. We're looking that to contain this pollutant in the next 18 samples. So out of 18, we're looking for exactly 2 samples having the pollutant. So in this case, what we're looking for is bad, but that's our success. We want to find it. That's what we want to find. So even though the pollutant is bad, you could flip this on its head and say, what's the likelihood that they aren't polluted? That becomes a 16, right? Instead of saying 2 polluted, if I'm looking for the inverse of that, saying that I assume 2 are polluted, I want to see the likelihood that 16 are not, I can take that inverse. But part of reading these binomial questions is determining what is a success. What are we looking for in an outcome? And here we're looking for the fact that it contains a pollutant. And so it has a 10% chance of containing the pollutant. And so I do that 0.1 to the x. And so here x is 2. And then I do 1 minus p, so 1 minus 0.1 to the n minus x, 18 minus 2. And we put that math in and we get that answer, 0.2835. Or we throw it into Excel and we calculate it with this function. And you can just type it in. You don't need any data there. You can just type equals binomial. Let's just do it real quick. So I can go to my formulas here. And if I look under more functions and statistical, I can find binomial. And so you see here how it shows, oh, you can't see it because it's super fuzzy and small, but it actually says number S, trials, probability of S, and cumulative. And that's that true false statement. It's assuming that it's cumulative. If you write false, then you're looking for the probability distribution function. So if I put that in, it's already put in the correct formula. And so now I can type in the information. I have 18, I'm looking for 2 pollutants in 18 trials. The probability is 0.1, and my logical expression to this is false. So I can enter it in that way, and it'll give it to me there. Also, if I just type equals and I start typing binomial, it should come up as your f of x there. And it gives me, again, Excel will tell you, you need to enter the number of successes that you're looking for. That's why it says n underscore s, number of successes. So I'm looking for 2 successes out of my 18 trials, 118, out of my 18 trials. And here I'm going to go ahead and do a cumulative distribution function instead, 0.1, and then I'm going to write true, or I don't have to write anything at all because the default is going to be that it's cumulative. Oh, you are going to make me write true. That must be, I don't know if it's the 365. But its default setting is true. And now I'm looking at the cumulative distribution function that I have up to and including 2. All right. We will do I call them case studies, but we'll be doing Excel and Minitab work once we're doing our continuous distribution functions as well. So we'll go back and do the discrete distribution functions, and we'll do the continuous as well. And we'll practice all of the Excel and Minitab functions for each of these distributions. Because on the FE exam, you need to be able to solve these problems by hand, I also require you to solve them by hand on exams. So to make sure that you know how to do it, I included on the exam doing it by hand. In our case studies, we'll use Excel or Minitab to solve these things for us, so we don't have to do it by hand. All right, so we're going to calculate these probabilities, and we have 0.01 as our probability of success, and we have 10 trials. And so we're going to look at the probability of getting 5 successes, of getting less than or equal to 2 successes, of getting greater than 9 successes, or getting 3 to 5 successes. So inclusive of 3 and up to 5. All right, we might change that problem to make it 2 so it's easier. Okay, so let's switch back. This is in your packet. And please tell me when I'm writing off the page. So the probability that x is equal to 5 for my binomial is going to be 10 and 5. And then that's to the 0.01. So that's my probability of success. And so my probability of success is to the x, and then my multiplied by my probability of failure, 0.99 to the n minus x. So that's also 5. And so if I put this in Excel or my calculator or anything like that, I'm going to come out with 2.4 times 10 to the negative 8. Now, looking at the probability that x is less than or equal to 2, this is actually the summation that x is equal to 0 plus x is equal to 1 plus x is equal to 2. So I actually have to do 3 different equations to calculate this when I'm doing it by hand. This is a great one to throw into Excel and say true and have it do it for you instead of having to do the 3 equations. So this is 10 total trials, with 0 successes. And so that's 0.01 to the 0, which is 1, times 0.99 to the n minus 1, which is, or n minus 0, which is 10. I'm going to add that to 10 over 1, 0.01 to the first, times 0.99 to the 10 minus 1, which is 9, plus 10 over 2, 0.01 to the second, times 0.99 to the n minus x, which is 8. So all of this comes out to be 0.9999. And the probability that x is greater than or equal to 9 is actually equal to 1 minus the probability that x is equal to 9. Oh, I'm sorry, this is out of 10 trials. Well, I can do it both ways. I can do it either way. This is also the probability that x equals 9 plus the probability x equals 10. On my continuous, I would have to do it as 1 minus the probability that x is less than 9. Because for continuous, there's an infinite realm between these. For discrete, I can do the actual addition. So this is 10 over 9, 0.01 to the 9th times 0.99 to the 1 plus 10 over 10 times 0.01 to the 10 and 0.99 to the 0th power, which is equal to 1, as we remember. So this whole term becomes 1, so that's easy. And this is 9.91 to the 10 minus 18th power. So the probability that x is between x is greater than or equal to 3, but less than 5 is really meaning the probability that x is equal to 3 and the probability that x is equal to 4. That's what we're looking at. Those are the numbers included in that set. So again, I have 10 and 3, 0.01 to the 3rd power, which is 0.99 to the 7th power, plus 10 and 4, 0.01 to the 4th power, times 0.99 to the 6th power. And this is equal to 1.138 times 10 to the negative 4th. So you'll have a question in your homework that will be very similar. It'll give you a couple different versions, equals to, less than, greater than, and a range. Did I write down something wrong? It happened. I just saw you asking, did I write, okay. No, so sometimes I copy things down wrong. I have all of it done in advance and I've checked it all. So everything should be right, but there are times that like, I just transpose numbers and copy things down wrong. If I do that, call me out so that I don't confuse people. Okay, so that was all binomial. How's the geometric different? Well, the binomial has fixed number of trials with random number of successes. Geometric has a random number of trials with a fixed number of successes. And for the geometric, we're looking specifically for the first success. So if the problem tells you that you have a series of random independent trials, and you're trying to find the number of trials until you get the first success, the number of trials, the number of times you have to try to do something until you get that answer. It's a simplified version of the binomial, because instead of looking at a various number of trials, I'm just trying to find how to get one success. I really don't care about failures, right? I'm just trying to get that one success. So what do I have? Well, I'm looking at the number of trials. So x to the minus 1 power. So these are all of my failures. The 1 minus p to the x minus 1 means every other single trial is a failure. And those come first in the sequence. And then bam, I finally get a success. This is my p. So this should remind you of chapter 2, where we were just multiplying. Remember, we said absent, present, 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 absent, present, 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 absent, right? Like we just kept adding p's to find the first time that there is a particle, I think, absent. Whatever the example was. That's the same thing written in formulaic form, and it's called a geometric distribution. So it's a derivative of the binomial because we're trying to count the number of trials. We're not counting the number of successes. We have a fixed number of successes that we want, and we only want one. So if you get a success in the very first trial, right, your X ends up being 1 and you got a success. So you could calculate that. What's the probability that I get a success the very first time I do it? So like the probability of me making a half court shot is 0.000001. Like what's the likelihood that that happens on my first try, right? It's not completely outside of the realm of possibility. It could theoretically happen. It's just not very likely to happen. Well, what's the likelihood at that probability that the very first time I attempt it, I get it? It's going to be very small. It's going to be very, very, very small number. How many trials will it take for that to happen? I have no idea, but it's a lot. We can calculate that with a geometric distribution. The variance and the mean here, this should, so instead of having the expected value be n times p, this is just 1 over p. The n was a function of our trials, right? Our n was our function of trials. Our p is our probability of success. Well, here we're just looking for that first success. So our expected value is 1 over p. And then our variance is 1 minus p, which is our probability of failure, divided by p squared. If you would like to see why those maths work, you can look in the textbook where they derive these for you. The negative binomial is the geometric distribution, but instead I'm looking for a value of successes that isn't 1. So if you look here, it's the exact same formula, but now I'm counting the combinations of the number of trials required to get to the number of successes that I'm looking for. So if I said, you know, how many trials are required for me to make 3 half-court shots with my probability of success being 0.0001, right? Like now I have a number that's not 1. And so you see the derivation here, it's very, very similar. It's Bernoulli trials, just like our binomial. So we have the 1 minus p to the x minus r, because x is counting the number of trials and R is the successes that I've been determining. And then I have the probability of success to R, which is the number of successes. So again, it's doing that counting sequencing that we had done all the way in chapter 2. But in this case, we're looking for a given number of successes and we're counting the number of trials. So the question might be, what's the likelihood, like how many trials are required for 5 successes to occur, with the probability of success being a given number? So when you're looking at these, it might be helpful to write down on your paper, which I wrote down on my paper. Just to remind ourselves. So the binomial, I'm looking for number of successes in a given amount of trials. So my number of trials is the given information. And I'm trying to figure out how many successes are going to happen. If I flip a coin 50 times, how many times will I get a heads? So my number of trials is what's given, and I'm trying to see how many successes occur. My geometric is number of trials needed to get 1 success. So in this case, the number that I'm trying to find is how many trials does it take? And then my negative binomial is number of trials to get R successes. R is what's used in the formula. So in a binomial question, I'm going to be given a number of trials and I'm trying to find the number of successes. In a geometric question, I'm going to be asked how many trials until I get the first success. In a negative binomial, I'm going to say how many trials to get 7 successes or 12 or 2, right? So they're going to have to give you the number of successes that you're looking for. So you're still looking for a number of trials, just like you are in the geometric, but they're going to give you a number that is not equal to 1. All of these cases are derivations of that Bernoulli expansion that gives us our binomial, right? So we have a probability of success and a probability of failure, only 2 states. All of these cases, you're only going to be given a probability of success or a probability of failure. If you're given a probability of success, you need to do 1 minus p. If you're given a probability of failure, you've been given 1 minus p. You need to know p, right? So you're going to be given a variable, either a probability of success or a probability of failure. From that, you'll know the other one. And you're going to either be given a specific number of trials or a specific number of successes. Choosing the correct formula is the key. On your exam, you will get 2 of these. One of them will be a binomial. One of them will either be a negative or a geometric. All right. So we have the f of x for this, and the derived expected value and variance are r over p and r times 1 minus p. So number of trials times the probability of failure divided by that p squared. This looks exactly like your geometric, but the geometric was 1 over p, right? Because we were looking for the probability, the number of trials to get that 1 success. Now we're looking for R number of successes, right? So instead of 1 over p, I have R over p. And instead of 1 minus p over p squared, I have R times 1 minus p over p squared. So you can see the relationship between the two. The biggest issue that people have is choosing the right formulas. Which one is this? Is this a negative, or is this a geometric, or is it a binomial? That's the biggest issue people have with these questions. The math is easy. Okay, so they give you an example here. What is the probability that the third failure is obtained in 5 or fewer tests? I'm given a probability of success, but what I'm actually looking for is failures. What I'm counting is failures. So my counting of failures means I take my probability of success and I subtract it from 1. So my probability of a failure is 0.2, but that's what I'm looking for. So I want to use the 0.2, not the 0.8. And then I'm looking at all of these conditions up to 5 tests. What's the likelihood that I have 3 failures within that time? And so it's a negative binomial. I'm given an R, I'm given a P, and I'm given an X. So my X is counting 3 trials, 4 trials, and 5 trials. Because I can't have 3 failures in only 2 trials. I can't have 3 failures in only 1 trial. I can't have 3 failures in no trials. I have to have at least 3 trials for me to get 3 failures. It might happen in 3, it might happen in 4, it might happen in 5, it might happen in 12. I don't know. We're checking the probability that we have 3 failures in 5 or fewer trials. So I'm going to sum up each of these possible conditions. So I have the sum that I am looking for. And so you see that I have my x minus 1 So we're following the formula that we have, x minus 1 over r minus 1. And so the r minus 1 is going to stay the same in every one of these cases. That r minus 1 is 3 minus 1. So r is 3, 3 minus 1 is 2. So that r of 1 is not going to change for each of these formulas. My x minus 1 is going to change because I'm summing where x is 3, x is 4, and x is 5. And so I multiply all of this out, and I can see that my when x is equal to 3, that 3 minus 3 becomes a 0 term, and so that goes to 1, and the 2 to the third, that is going to be calculated multiplied by 1, and that 3 minus 1 over 2, I have 2 over 2 factorial, so that goes to 1. So the only term I have left is the 0.2 to the third power. And then I calculate for the value where x is equal to 4 and where x is equal to 5. And so those are the other two. I sum all of those up, and that gives me the probability that x is less than or equal to 5, or the probability that I have 3 failures in 5 or fewer trials. And it's 0.058 is my probability. So that's what an that's an example of what a question would look like. So a probability a person carries a gene for a disease is 0.1. People are assumed to be independent with respect to the gene. What's the probability that 4 or more people need to be tested to detect 2 with the gene? And then what is the expected number of people to test to detect 2 with the gene? So go ahead and start this example on your own, and then we'll look at it together. And I'll pause the recording. So let's start with part B first, because it's really easy. So my expected value, my formula for the expected value of a negative binomial is just R over P. And so my R that I'm looking for is given to me as two successes, 2 people have the gene. My probability of success is 0.1. And so that is 20. Now this is kind of interesting because this is saying that how many people do I need to test to get to 2 with a gene? 20 people. So now I'm looking at what's the probability that 4 or more people need to be tested to get those 2. So it's kind of interesting comparing the expected value or the probability. So probability of 4 or more. So our given statement here, we know that we are working with a negative binomial. So we know that our formula is that the probability that x is equal to a certain value is going to be equal to x minus 1 over r minus 1. That is our base formula. And that's for the permutation there. And then we have 1 minus p to the x minus r multiplied by p to the r. So that's my given. That's where I'm starting, is with the negative binomial. Then I'm also given my probability that someone has a gene, which is what I'm looking for, is 0.1. And I'm looking for the number of successes, the number of successful tests. I am looking at what the probability is that I need 4 or more trials to find 2 different people with the genes. So I'm looking for 2 successes. And the question is asking for what's the probability that x is greater than or equal to 4. Now I can't really find that, because out of what? Like, what's my cap? How many total people would there be? Well, I mean, theoretically, like, we could test all of Vanderburgh County or something. We could test all the students at USI, right? Like, I haven't been given a cap, which means what I'm really finding is I'm finding 1 minus the probability that x is less than 4, but I've got to have 2. So x is never going to be 0, right? Because I can't find 2 successes in 0 trials. And x is never going to be 1 because I can't find 2 successes in 1 trial. So once I take out the impossible sample space, my null sample space, what I have is I have 1 minus the probability that X is equal to 2. So I test 2 people and then I find 2 people with the gene. That sounds really small, by the way. Plus the probability that I test 3 people and 2 of them have the gene. So this X equals 2 and X equals 3 is really what this X is less than 4 once I take out the impossible sample spaces there, right? So 1 minus this is equal to this unbounded upper limit. Does that make sense? So now I know that I'm really looking for 1 minus X equals 2 and X equals 3, and I have my formula for finding X equals 2 and X equals 3. So now I can just put those in this. So now I have the probability that X is equal to 2 is going to be, thank you. So my X minus 1, so this is X is equal to 2, so that's 2 minus 1. And my R is 2, and that's 2 minus 1. And then my 1 minus P is 0.90 to my X minus R. So I have 2 minus 2, so that's to the 0th power. And then my P, 0.1 to my R, 2. And this is equal to 0.01 because all that stuff canceled out. And then the probability that X is equal to 3 is equal to, again, my X minus 1. So 3 minus 1. My R minus 1 is still 2 minus 1. Then my 1 minus P is 0.90. The X minus R is now 1. And my P is 0.1 to the Rth power is 2. And so this is equal to 0.018. So the probability that X is greater than or equal to 4 is equal to 1 minus 0.01 plus 0.018. And this is equal to 0.972. So there's a 97% chance that you are going to have to test more, 4 or more people to get 2 people that are positive. Which makes sense. It should be a big number. This is actually a little smaller than we expect, right? Because if we see that the expected number of people is 20, then the probability that just 4 or 5 or 6 people is pretty small. All right, so that's how those questions work. The last discrete distribution that we look at in this class is the Poisson distribution. And so for the Poisson distribution, we have things to the power of E, and we have a lambda value. And the lambda we're going to see is a rate. So a Poisson process is a probability that something happens at a given rate. This could be a rate of time, this could be a rate of distance, this could be a rate of flow, right? There's a lot of different things that have rates. But Poissons are really, really helpful when we're looking over a given stretch of something. And so that lambda t is a rate at which something happens. And so our random variable x, we see the distribution is equal to e to the negative lambda t times lambda t to the x over x factorial. So we see that we have a length of wire, and we have an average number of flaws is equal to 2.3 per millimeter. So find the probability of exactly 10 flaws in 5 millimeters of wire. Well, so I'm looking over a specific length of something. And so I have a physical length, millimeters, And so my lambda t, my probability, the rate at which something happens is 2.3 flaws per millimeter. I'm looking over a stretch of 5 millimeters of wire. So my first thing in this formula is to figure out my lambda t, and that's going to be 11.5 flaws. That's the rate. So what's the probability of exactly 10 flaws in that given length of wire? I have e to the negative 11.5, and then I have 11.5 to the 10th over 10 factorial. And sorry, it kind of comes out weird. The divisor symbol didn't go the whole length of that. Sorry about that. And so that equals to 0.113. So if I wanted to find the probability of at least one flaw in 2 millimeters of wire, I'm looking that the probability is greater than or equal to 1. So that's 1 minus the probability that it's equal to nothing. And so again, I convert that rate, 2.3 flaws per millimeter of wire. I'm looking at 2 millimeters of wire. So my rate, my lambda t is 4.6. And so my formula, when x is equal to 0, all of those terms drop out, the lambda t to the x over x factorial, all that stuff falls away. So the only thing that's left is e to the negative lambda t, or 1 minus e to the negative 4.6. So what's the probability of having at least one flaw? It's 1 minus the probability of having no flaws, or 0.9899. The mean and the variance are equal to each other in this specific case. And so lambda t is the mean and the variance. Again, you can look at the textbook to see the derivation of why this is true. So if you have a mean of 25 particles per square centimeter, the variance is also 25 particles per square centimeter with a standard deviation of 5, because the standard deviation is still going to be the square root of the variance. That is always true. So the mean and the variance are equal to each other. It makes, this is why we have, you'll notice that for the Poisson, the shape of the curve is an exponential function. So it's just exponential, and that's why that's true. So when we're looking at a goodness of fit test for a Poisson, that would be one of the things that you could measure. You could compare its mean and its variance. And if its mean and variance are very, very close to one another, you're probably looking at a Poisson function for your data. Now, because we're also going to use Minitab, we could also just do our goodness of fit test, and we put in the data and we say, Minitab, you tell us what it is. And he'll come back and he'll tell you whether it's a normal, binomial, geometric, or Poisson. Like, he'll tell you whether or not what it is. But that's a way that you can actually use your descriptive statistics. And so you take a set of data in Excel, you run your descriptive statistics, you compare your mean to your variance. And if they're really, really close to each other, you're looking at a Poisson function probably. So it's helpful to know that. And so we're going to do just a couple examples, and we'll do this together so that you all have practice working through these different potential outcomes. And we're done with the packet. Okay. Oh, this is really, let me do it this way. Casting a really big shadow on my notes. Okay, there we go. So the first one is for a value, find the probability that x is equal to 0. And so it's giving us, it says that the mean, which is equal to the expected value, which is equal to lambda t. So when it says the mean of x is equal to 4, then my lambda t is equal to 4. Also, my sigma squared would be equal to 4. That's what I know about the Poisson. So it's already given me my lambda t. I didn't have to solve for that first. And so now I'm just doing the formula. And so I'm doing e to the negative lambda t multiplied by lambda t to the x over x factorial. So I have e to the negative fourth times 4 to the 0, that becomes 1, over 0 factorial, that becomes 1. So I just have e to the negative 4, which is 0.0183. The probability that x is less than or equal to 2 is equal to the probability that x is equal to 0 plus x is equal to 1 plus x is equal to 2. I've already solved for x is equal to 0, but this just came out to e to the negative 4 because everything else cancels out, plus e to the negative lambda t to the x over x factorial, plus e to the negative lambda t to the x over x factorial. All of those things, when you throw them in your calculator, come out to 0.2381. I think this was meant to be an x is greater than 4 and do the 1 minus x is less than 4 again. I don't know why we would do 2 of equals to each other, but p for x is equal to 4. Again, we're just doing the same thing. So we have 4 to the negative 4 times 4 to the fourth power. I'm sorry, e to the negative 4 over 4 factorial. And that is equal to 0.1954. The big thing with the Poisson, it's very mathematically simple. The big thing with the Poisson, usually on homework and exams or quizzes, is just simply calculating your lambda t correctly, making sure that you've taken care of the rate. When they give you the mean already, like they've given you the hardest part, and then it's just plugging and chugging in your calculator. All right, that is it. I will see you next week.